Hello everyone, good morning. So thank you very much for attending my presentation. My name is Shahinuzzaman. I am a PhD student, third year PhD student in Concord University under Professor Chen. So today I am excited to share my research topics is pixel-based RAS severity classification on steel surface using ASSI feature and machine learning techniques. As we know, the rust is the sub-branch of the corrosion. According to the National Association of Corrosion Engineers, the estimated cost of the corrosion is 2.5 trillion US dollar, which is equivalent to 3.4% of total global GDP. This is the huge impact in global GDP. Beyond the economic cost, rust can significantly affect on the structural integrity, safety, and the risks. Let me share one real example. I consider the Quebec bridge. This bridge is the world's longest cantilevered steel bridge. This bridge was failure in 1960. The primary reason due to the lack of proper monitoring of this bridge. Also, this bridge was covered, 60% covered by corrosion. So from this motivation, I fixed my three research objectives. The first one, prevent catastrophic structural failure caused by rust defect through early detection. And second objective, generate the synthetic training data for machine learning to overcome to data scarcity for the rust. My last research objective, to enhance the inspection accuracy and minimize human error through the automatic system. So before going to my main methodology, I would like to share basic knowledge or basic fundamental concept about my research. Let's discuss about the computer vision techniques. So computer vision techniques can analyze your digital image based on the feature. So computer vision techniques are mainly classified or divided into four parts: classification, detection, segmentation. As we can see, what is classification? See, classification is classify your object based on the group. As we can see, the first image, there is a person, sheep, and dog. The second technique is object detection, also we call object localization. So computer vision techniques can identify your object by bounding box, also can identify exact location of your object. Third one is segmentation. Segmentation is pixel based, segment your object. So segmentation are divided into two categories: the semantic segmentation and instant segmentation. The semantic segmentation gives you the each pixel based level without difference between the same group. But instant segmentation is the same thing, but is difference within the same group or same cluster. As we can see, the semantic segmentation, all sheep are same color, but instant segmentation is different color. So let's discuss about the color space. This is a very crucial role in this research. So there are so many color space in this research, but most commonly used color space is RGB, SSI, and LAB, and each word indicates the meaning. For instance, RGB indicate red, green, and blue. SSI indicate the hue, saturation, and intensity. So in this research, we utilize this color space SSI. So each color space has a different shape. For example, the RGB has a cubical shape. The SSI color space, the cylindrical shape. Also, there is a three-coordinate, three-dimensional cubical shape. So we can find out our color by identifying the three-coordinate value. For example, the coordinate value is 100, means this color is totally red. This coordinate value 010 means it's totally green. So if we know the three coordinate, so we can figure out the which color holding in our image. Oh, sorry. So normally, our color images are holding the 8 bits. So 8 bits equivalent to 256. This value range 0 to 255. And also there could be more bits, but for example, the 16-bit is normally used for high density resolution. Also, the 24 bits also image can be used for the video. But our research based on 8 bits, the total number of color is 256. So this is my main methodology. I divided this methodology to phase. This is the phase 1. The phase 1, its main object is identify numerical value for the pixel, raster pixel. So first, we converted our RGB image to HSI color space, and then we use k-mean cluster through the elbow method. So elbow method can identify optimal number of cluster. And then we check them manually also. And then after we conducted histogram analysis, and then we calculated our mean with standard deviation pixel value for our object raster. So we use this formula to converted our image from RGB to ASSI, because I mentioned before in this research we use ASSI color space. This is the hue, saturation, and intensity. As we can see, this first image is our original RGB image, and we converted HSI color space. This one is AS, hue, saturation, and intensity. And also, the literature review shows that the hue property of HSI color space can minimize or eliminate the shadow or illumination problem from the image. That's why we choose the HSI color space. Also, this is the cluster has been done by k-mean clustering. We also use the elbow method. As I mentioned before, elbow method can identify the optimal number of cluster in your image. So according to the ASTRO guideline, in this research, we consider 3 category of RAS. So we consider, like, this is the original image, this is the cluster 0, cluster 1, and cluster 2. So each cluster are indicate the each severity. And then we conducted histogram analysis based on the cluster. In this slide, we consider only 2 clusters, cluster 0 and cluster 1. So histogram analysis is process to identify your object frequency. As you can see, this is the cluster 0 for hue properties. This red value is close 0 to 10 or to 20, something like this, or the saturation and intensity. Also, we have done the same thing for cluster 1. So this table is summarize of our pixel value from the ASSI color space. This is the mean value with our standard deviation for the 3 category of RAS. As you can see, our hue shape is circle, so hue value should be 0 to 360, sorry, and S and I range should be 0 to 1. So this is the color histogram for all images. So this is my methodology phase 2. While in phase 1, we use the unsupervised machine learning like k-mean clustering and elbow method. But in phase 2, we use the supervised machine learning like random forest. So we generated synthetic data from the pixel value with standard deviation that we got this value from the histogram analysis. And then we use the random forest classifier and classify our raster according to the guideline. So this is the how we created a synthetic data set. Like we have a mean and standard deviation pixel range from the histogram analysis, and creating synthetic data and then apply the machine learning model. And then as we can see, our result F1 score is 75%, precision 74%, accuracy 81%. So this slide shows the outcomes from this process. And as we can see, this process can identify the raster severity. So as we can see, there's a red color indicate the severe raster, yellow color indicate the major raster, and the orange color indicate the minor raster. So this is my main contribution. So we use the both supervised and unsupervised machine learning in this research. Also another main contribution, so due to limited data availability of RAST in online, we try to develop the synthetic numerical RAST data to enhance the model machine learning. And third contribution, we use the ELBO method to find out the optimal number of cluster in the image. For sure, there should be some limitation, but it's a main limitation. So in this research, it allows only 30 real world images for the histogram analysis. Based on this 30 images, we have finished the phase 2. This is the main constraint or limitation. The second is our model accuracy. There should be a room to improve our model accuracy. So thank you very much.